Hello, 102 students. Let me give another go around here for another question in Chapter 7. This one is actually in the exercises, so it's designed to be more of a calculation one. So let me grab my calculator here and kind of clean off the screen and get ready to use it. But again, let me illustrate that I think a good way to approach these problems is to start off by saying the initial energy is equal to the final energy. So again, this chapter is all about work and energy and the most important principle of conservation of energy. And like I said on the other video, there's three important conservational principles. The first being momentum, which was Chapter 6. The second one we're doing now in Chapter 7, which is conservation of energy. And we're about to see a third one called conservation of angular momentum. A little bit harder stuff when things rotate. And so that's coming up next week in Chapter 8 here. But just like I would make kind of two columns for conservation of momentum and say initial and final, or I think I did kind of a before and after, they are just equal. So there's a little equal sign. So take advantage of that. And so let's read this problem. Number 5 says we have a 4 kilogram car with a speed of 5 meters per second, and it collides head on with a stationary 1 kilogram car. Now, after the collision, the cars are then locked together with a speed of 4 meters per second. How much kinetic energy is lost in the collision? All right, so the three energies that we're dealing with so far, and let me emphasize there are more and we'll be introduced to more as we move along, like solar energy and nuclear energy and chemical energy. But they are kinetic energy and potential energy and also heat. And so heat is really kind of measured as how much additional is created from the before to the after, or the initial to the final. So I don't usually put heat on this side, but what this is really saying is if I take the kinetic energy initial and the potential energy initial, that's got to equal the kinetic energy final, potential energy final, and then the heat that's generated, if any, during this process. All right, so if I'm reading this right, there's nothing about going uphill or downhill. And so the equation for potential energy is mgh. Presumably this is, on some kind of level ground that will define that h to be 0. Even if we define it as non-zero, so maybe the floor is 0 and it's up on a table, so it's a meter high. Whatever that is, it's the same on both sides of this equation. So they're going to cancel off, either by saying they're both zeros because it has no height, or by saying it has some height. And when you put that number in, it's going to be the same number on both sides. So this problem doesn't have any potential energy in it. Now, it does have kinetic, and it does have two objects. So I probably should write this as kinetic energy initial number 1 plus kinetic energy initial number 2 must then equal kinetic energy final number 1 plus kinetic energy final number 2, and then plus any heat that is generated if these things rub on each other. And since we have a collision, they definitely rub and hit, and there's going to be some heat here. And that's what they're really saying. How much lower is this compared to this? That really how much heat is then created in this. Okay, so the first one, when it says it has a 4 kilogram car with a speed of 5, would look something like this. We would go 1/2. We'd put in our 4 kilograms. We would put in our speed of 5 meters per second, and we would square it. And then the second one says it's stationary. So stationary would mean 0 speed. So if you maybe I should have put the formula up here. Kinetic energy is 1/2 mv squared. You put in 0 speed, you get 0 kinetic energy. And of course, obviously kinetic energy is energy of motion. So if they're not moving, if this second one is stationary, it has none. All right. So the left-hand side of the equation would be something like this. 5 squared is 25. Half of 4 is 2. So 2 times 25 is 50. And the units then would be a kilogram meter squared over second squared. The first meter would make that a Newton times a meter would make it a joule. So sure enough, they're really trying to say, before the collision, the total energy is 50 joules. And it happens to all be in car number 1 because car number 2 has no energy. Now, after the collision, so let's do this, 1/2, and the original 4 kilogram car, now stuck together with the 1 kilogram car, is moving at a speed of 4 meters per second. And since they're stuck together, I would say now that the 1 kilogram is also moving at 4. And then there's what I'd like to find, the difference between these starting kinetic energies and these endings. That's the heat. All right, so right here, 4 squared is 16. This would be a 2. So 16 times 2 is 32. Yeah, this threw me off a little bit. So that was a 50. Yeah, okay, so 16 times 2 is 32. And then the units still come out to be a joules, okay, plus. And then over here, same idea, 4 squared 16, that's a 1. Half of that, 16 is an 8, so this is 8 joules, and then the heat. Put that together, and of course that's a 40. Subtract it off from there, and you got 10. So the ending kinetic energy right here is 40. That is lower by 10 compared to the 50. So the loss in kinetic energy is 10. Or put another way, the amount that is converted into heat is the 10. That's the heat. That's the loss in kinetic energy. That's where it went. Again, notice this principle of conservation of energy. Again, hopefully that was helpful.